assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
This question asks us to consider a reaction where H2 combines with I2 to form 2 moles of HI. It tells us that the mixture at equilibrium has the following pressures of each of the gases, and that it tells us there's a second mixture that has different pressures for each of the gases. And the first question asks is the second reaction at equilibrium? So above this horizontal line, I have what it says are the equilibrium conditions. It says at equilibrium at 175 Kelvin, the pressure of H2 is 0.958 atmospheres, the pressure of I2 is 0.877 atmospheres, and the pressure of HI is 0.02 atmospheres. Here's the equation for the equilibrium constant with respect to pressure, or Kp. It's the partial pressure due to HI squared, because there's a 2 here, divided by the product of the partial pressure of H2 and the partial pressure of I2. If you plug in each of the numbers it gave us, 0.02 for HI, and 0.958 and 0.877 for H2 and I2 respectively, you would see that the equilibrium constant with respect to pressure of the equilibrium at equilibrium is 4.76 times 10 to the negative fourth. So that's one bit of information. Then it asks, is the second reaction at equilibrium? And it tells us the pressures of each of the gases under these conditions. It tells us that H2 is 0.621 and I2 is also 0.621 and HI is 0.101 atmospheres. If we plug these values into the same equation to calculate partial pressure with respect to P, or Kp, we would see that its equilibrium constant, or this would be the reaction quotient, or Q really at this point. So I'm going to write this as a Q is 2.65 times 10 to the negative second. We can tell that these two numbers, of course, are not the same, and this is actually much larger than the equilibrium constant with respect to pressure. So when Q is greater than Kp, we know that the reaction is going to run backwards. I'll say that again. When Q, or the reaction quotient, is larger than Kp, it favors the reactants, and the reaction will run to the left or backwards as it's written here. And so that answers the first question. No, it's not at equilibrium, but now it wants to know, once it does get to equilibrium, what will the partial pressure of HI actually be? So I've set up the beginning of an ice table here. Let's finish it. So I said that the reaction is running backwards. So normally when we write it up, we write minus for each of the reactants. But since we know it's moving to the left, these changes will be positive for the reactants, and they will be negative for the products. Because we're going to go backwards and take HI and form H2 and I2, we're going to lose HI, and we're going to gain H2 and I2. Additionally, we'll lose twice as much HI as we will gain for any one of the two reactants because of this 2 here. So we can write the equilibriums as 0.621 plus X. Same thing for I2, 0.621 plus X, and 0.101 minus 2X. Now we just got to plug these into the equilibrium equation. If we do 4.76 times 10 to the negative 4, since that was Kp, set that equal to, and we just plug in these numbers into this equation, we would get 0.101 minus 2x squared. The denominator is going to be 0.621 plus x plus 0.621 plus x. So I'm going to write that as 0.621 plus x squared. So writing them both out side by side. Normally when you do these types of equations, you try to solve the quadratic equation. That's not necessary here because you can just take the square root of both sides and just get x's by themselves. We don't have any x's squared, so this is just a simple algebraic equation to solve. If you worked it out, I won't, for time and space, you would get that x equals 0.043. And then if you plug this in here, you would find, try to draw an arrow here, you would find that the partial pressure with respect to HI, so if you plug 0.043 in for x here, you solve this, the partial pressure would be, let's see, I just had it here. All right, sorry for the delay. The partial pressure would be 0.014 atmospheres. So just to summarize, we found that this condition was not at equilibrium because its reaction quotient was greater than the equilibrium constant. That tells us the reaction is going to shift back towards reactants to reach equilibrium. So we're going to gain some amount of each of the reactants here and lose some of the product HI. If we plug this into the equilibrium constant equation, we could solve for x here and write equal sign x equals 0.043. We'll plug that back in here to the equation we got for the equilibrium constant partial pressure of HI. We found that the partial pressure of HI was 0.014 atmospheres.